Here we have a crazy function. F of x is inverse tangent or arctangent. I could have used an arctangent, and you should be ready for that in the gateway to see an arctangent instead of an inverse tangent of cosine of e to the x squared power. That's a composition of four functions. X squared is the inside function, e to the x is the next most inside, then cosine, then inverse tangent. This one we have a quotient, so we also need the quotient rule. In the top, we have a composition, so we need the chain rule as well. And it's probably best to write the bottom there as x to the 3/2 power and use the power rule when we differentiate the low in using the quotient rule. So just take it step by step. The derivative of inverse tangent, what is that? 1 over 1 plus x squared if it's just a plain x, inverse tangent of x. So you start writing that 1 over 1 plus x squared, but then you say, hey, well, hold on a minute. That's not just an x there, it's a cosine of e to the x squared. So that entire thing needs to be squared. For emphasis, I'll put parentheses around the whole thing. It would technically be okay to put that 2 above the cosine. It's understood standard notation. When you write cos squared, it means cosine quantity squared. But don't forget to multiply times the derivative of that inside function, the cosine of e to the x squared, which I need the chain rule for again. Now I'm ignoring the inverse tangent. The derivative of cosine is negative sine. You do need to put a dot there for sure, and I'm putting parentheses here for extra emphasis. I'm multiplying this entire fraction by whatever I put inside the parentheses. The derivative of cosine is negative sine of x, but wait a minute, it's e to the x squared inside there, so I have to plug in the inside function. Then multiply times the derivative of that inside function. Notice the extra sets of parentheses here are pretty essential. I'm only taking the sine of that. The derivative of e to the x squared goes outside that. I need the chain rule once more. The derivative of e to the x is e to the x, but plug in x squared, then multiply times the derivative of x squared, which is 2x. So that entire thing is the derivative of this piece. We also need to take the derivative of this fraction. That's a quotient. Low d high minus high d low over the square. What's below? Low, which I can write either like this as x square root of x or as x to the 3/2 power. D high, I need the chain rule there. The derivative of inverse sine, also called arc sine, is 1 over square root of 1 minus x squared. 1 over square root of 1 minus x squared, but I've got a natural log in there, so that's got to get squared. Extra step, don't forget with the chain rule to multiply times the derivative of that inside function. The derivative of natural log of x is 1 over x. That's low d high, not done. Minus high d low, and for the derivative of the lower function, I'll think of it as x to the 3/2, and its derivative then will be 3/2 x to the 1/2, or if you prefer, 3/2 times the square root of x. Over the square, what's below? X to the 3/2 squared would be x cubed. So this crazy thing here, if I have not made a mistake, is the derivative of this crazy thing. This should be astonishing to you. This is so powerful. I don't need any limits. Heaven forbid I compute this with the limit definition of the derivative. No. I'm a mathematician and I never want to do that in my life. Even though I love math, right? I don't want to do that. I want to use these rules. These rules are super duper powerful. Has anybody ever done that with a limit definition? Probably not. Not even Newton. Here I'm going to enter it in Mathematica and double check it. Notice that inverse tangent is arctangent. Hang on a second here. Inverse tangent is arctangent. Inverse sine is arcsine in Mathematica. You've got to do that with the capital A and capital T here and the capital S here. There's a cosine with capital C. Here's the number E, capital E, raised to the x squared power. Ln of x, I mentioned this once in Mathematica, is actually log. I know, confusing. Mathematica is created by Stephen Wolfram. He's a physicist. Physicists tend to write natural log as log. Actually, advanced mathematicians do as well, because it's like, well, that's the best log, so why not just call it log? So there, that's the function. I enter it, and then here's f prime of x. It may not be simplified in the exact same way we did, but let's just see what it looks like. Okay, so I see a 3 arcsine, a negative 3 arcsine log over 2x to the 5 halves. That is essentially this part of the answer. Arcsine is inverse sine. You see the log inside there. The 3, the 2 can go in the bottom. You got the negative sign. X to the 1/2 can go in the bottom as an x to the negative 1/2. 3 minus 1/2 is 5 halves. Yeah, that first term is this part of the answer. This part right there looks like it comes from this part of the answer. X times square root of x is x to the 3 halves. Bring that in the bottom as a negative 3 halves power. 3 minus 3 halves. Wait a minute. Oh, we also have an is 1/2, but then this 1 over x can be brought into the bottom as well to raise the power of x by another 1 to 5 halves. And the square root can be brought into the bottom. Yeah, that's what that is. And then finally, this part is the first part we had. Negative, see a negative sign there. 2x e to the x squared comes from those. We see a sine of e to the x squared. And we see a 1 over cos of that thing squared. That's Mathematica's notation for squaring the cosine. Oh, okay. We could see what happens if Mathematica tries the limit definition of the derivative here. Probably will be unsuccessful. And probably Mathematica will spin its wheels. I would be surprised if it gets it. It's spinning its wheels. It's running. Who knows? Maybe someday it would get the answer, but how long that would be, I don't know. You can stop the evaluation by aborting the evaluation. That doesn't clear the memory. If you want to clear the memory, that's where you do the quit kernel. But aborting the evaluation will at least stop the evaluation. Can we graph this thing and its derivative? We can certainly try. Do I know what the graph looks like? I have no idea what the graph looks like. I do have a logarithm function in there, so I do need to plot this for positive values of x. I'll just try this. Make the original function blue and the derivative red. Maybe they're so complicated that's okay. Yeah, it's having a little hard time graphing it. Okay, very wild function. And it's kind of stalling on me. If it's stalling, you can always force quit, though. If you haven't saved anything, then that's trouble. Remember to keep saving things because Mathematica doesn't auto-save as far as I know. A little less crazy if we just go to 3. How about 1.5? Okay, not so crazy there. And the red graph, again, is supposed to be the derivative of the blue graph. Okay? You know, you can give functions names if you want. You can name them after yourself. I could call this Kinney of x, and I could try to patent it. And then anytime anybody wanted to use this function, they'd have to pay me money. But probably nobody would want to pay me money for that, because it probably doesn't have any applications. Anyway, it's still cool to see that we can find the answer. That's very, very powerful.